The cosmos is not a random splatter of stars. It is a grand, organized structure, the largest we know of. This is the cosmic web, a vast network of invisible threads that guides the placement of every galaxy. By the end of our journey, you will understand the hidden architecture that shapes the entire observable universe. How did microscopic ripples from the dawn of time grow into this billion-light-year tapestry? What unseen force acts as the universe's master builder? The answers lie in a story that stretches from the quantum realm to the edges of space. What does it mean to live inside such an immense and intricate design? Our story begins in a realm of unimaginable density and energy, a fleeting moment just after the beginning. In this first fraction of a second, the entire cosmos was smaller than a single atom, a seething ocean of pure potential. Here, the rules of our everyday world did not apply. Instead, the bizarre laws of quantum mechanics held sway, where empty space itself is never truly empty. It fizzes with temporary particles popping in and out of existence, creating a constant microscopic churn. This churn produced tiny, random ripples in the very fabric of spacetime, fluctuations on a scale so small they are almost impossible to describe. They were mere whispers in the quantum noise, utterly insignificant in that moment. But then, something extraordinary happened. The universe underwent a period of hyper-fast expansion called inflation. In an eye blink, it grew by a factor of trillions upon trillions. This explosive stretch did something crucial to those quantum whispers. It took those minuscule ripples and magnified them, stretching them across the cosmos like fingerprints pressed into soft clay, and then pulled to the size of a continent. What were once quantum quirks became the first large-scale features of our reality, faint hills and valleys in the density of matter and energy. This pattern, frozen into the universe as it cooled, became the primordial blueprint. It was not yet a web, not yet any structure we would recognize. It was simply a subtle map, a cosmic lottery ticket drawn at the moment of creation, dictating where, in the vast emptiness to come, matter would eventually begin to gather. This invisible imprint held the first secret of the cosmic web, a secret written in a language of density that only one force in the universe could read: gravity. Gravity is the universe's great storyteller, and it had a powerful new character to work with. That subtle map of hills and valleys, the magnified quantum whispers, was not made of the atoms that would one day form stars and planets. It was written primarily in a substance we cannot see. This is the unseen architect, dark matter. Think of it as the universe's hidden scaffolding, comprising roughly 85% of all matter. It does not shine, reflect, or absorb light. It interacts with our world through one force alone: gravity. This made it the perfect, silent builder in the early cosmos. While the hot, radiant plasma of ordinary matter was too energetic to settle down, dark matter, unaffected by light's pressure, could begin to gather immediately. Within those slightly denser regions of the primordial blueprint, dark matter particles started to drift together, pulled by their own collective gravity. Over hundreds of millions of years, this gentle accumulation sculpted the first large-scale structures in the universe, a vast, diffuse network of dark matter filaments stretching across the void. These were not solid threads, but rivers of gravitational influence, immense highways of unseen mass. The luminous universe we would come to see, all the stars and galaxies made of ordinary atoms, was merely a passenger. It was destined to follow this dark, gravitational lead, flowing along the invisible roads that dark matter had built first. But if we cannot see this dark scaffolding, how can we possibly know it is there? The story of the cosmic web is one of brilliant detective work, of astronomers learning to see by listening to the whispers of the universe. They map the invisible by observing its shadow, its influence on the one thing that does reach us across the void, light. One of the most powerful tools in this investigation comes from the most luminous objects in the cosmos, quasars. These are the monstrously bright cores of ancient galaxies, powered by supermassive black holes feasting on surrounding matter. They act as cosmic lighthouses, beaming intense light across billions of light years. When this brilliant beam journeys toward Earth, it does not travel through empty space. It passes through the diffuse, wispy gas that clings to the dark matter filaments of the cosmic web. This gas, primarily hydrogen, leaves a unique fingerprint. As the quasar's light passes through, atoms in the gas absorb very specific colors or wavelengths from that light. The result is not a single dark line, but a whole forest of them, thousands of subtle absorption lines etched into the quasar's spectrum, each one a record of a clump of hydrogen the light encountered on its long journey. A single quasar gives us a one-dimensional probe, a thin needle of sight through the cosmic haystack. But by pointing telescopes at thousands of quasars scattered across the sky, scientists gather thousands of these needles. Using immense computing power, they can stitch these one-dimensional probes together, performing a kind of statistical tomography of the cosmos. They can reconstruct in 3 dimensions the vast, sponge-like distribution of that hydrogen gas. And since that gas traces the underlying gravitational skeleton, this painstaking process allows us to paint, stroke by digital stroke, a portrait of the cosmic web itself. It is a map drawn not in ink, but in the missing light from countless distant beacons. This intricate map of light and shadow reveals a universe in a state of profound tension. For the cosmic web is not a static sculpture, but the visible evidence of an epic, ongoing struggle. On one side is the relentless pull of gravity, the force that draws matter together. On the other is the expansion of space itself, the foundational energy of the cosmos that continuously stretches the distances between things. The shape of everything we see, from the tiniest galaxy cluster to the billion light-year voids, is the direct result of this great cosmic tug of war. Think of the primordial universe as a vast, simmering pot of broth, with those quantum ripples creating slight variations in its thickness. In the thickest, richest patches, gravity had a powerful advantage. Here, the mutual attraction between particles was strong enough to overcome the stretching force of expansion. These over-dense regions acted like anchors, pulling the surrounding material inward. Over eons, this led to a dramatic collapse, the birth of the dense nodes where we find immense galaxy clusters today, cities of millions of galaxies bound in a fierce gravitational embrace. But in the vast, thin stretches between these anchors, the opposite occurred. Here, the density was so low that gravity's grip was exceptionally weak. The expansion of the universe, unimpeded, simply pulled these regions apart faster and faster. What began as slightly emptier patches were stretched into incomprehensibly vast cosmic deserts, the great voids that make up most of the volume of the observable universe. Within these voids, expansion is the undisputed champion, having swept space so clean that a single, lonely galaxy can be a rare and distant island. The most fascinating structures, however, are the ones caught in the middle. This is where the battle reaches a dynamic and spectacular stalemate. The material that was not quite dense enough to collapse into a node, yet not quite sparse enough to be swept into a void, found itself in a cosmic balancing act. Gravity was strong enough to prevent this matter from drifting away entirely, pulling it toward the anchoring nodes, but the expansion of space was also strong enough to prevent it from falling all the way in. The result is a stretch, a pull in opposing directions that elongates the material into the magnificent filaments we see bridging the gaps in the web. These are not static bridges, but flowing rivers of galaxies and gas, forever in transit, forever caught between the urge to coalesce and the force that seeks to tear them apart. This tense equilibrium defines the evolving architecture of everything. It explains why galaxies are not scattered randomly, but are strung along these invisible threads like pearls on a necklace, flowing toward the dense clusters at the intersections. The cosmic web is a snapshot of this universal contest, a frozen moment in a fight that has been raging for over 13 billion years. And as we look deeper, we must ask, what does this grand design mean for the destiny of the structures within it, and for the ultimate fate of the universe itself? The tension between gravity and expansion set the stage for the universe's first great act of architecture. Within those faint hills of dark matter, gravity began its patient, relentless work. But this gathering was not a simple, uniform collapse. Matter did not fall inward from all directions equally to form perfect spheres. Instead, it behaved much like water on a vast, tilted plain. Picture a landscape after a gentle rain. The water does not pool randomly. It seeks out the subtle grooves and channels in the earth, flowing along paths of least resistance, merging into streams that eventually feed rivers. The early universe operated on a similar principle, but on a scale so grand it defies earthly comparison. Those primordial overdensities were not isolated mounds, they were connected. Gravity pulled matter not just toward the center of each dense patch, but along the lines that linked them together. Imagine 3 strong magnets placed in a triangle on a table, with iron filings scattered between them. The filings would not just jump to the magnets, they would also align themselves into delicate chains stretching from one magnet to the next, tracing the lines of magnetic force. In the cosmos, dark matter was the unseen magnet, and ordinary matter was the filing, compelled to flow along the invisible gravitational highways that connected the densest knots. This flow, channeled and focused, is what sculpted the universe's first major features, the filaments. They are the cosmic rivers, the one-dimensional channels where matter found its easiest path. And as matter drained into these rivers, it left behind enormous, empty basins. These are the cosmic voids, regions hundreds of millions of light-years across that contain almost nothing. They are not true vacuums, but they are so desperately sparse that a single galaxy might be the only landmark for unimaginable distances. The birth of filaments and voids was a simultaneous event, 2 sides of the same cosmic coin. Where matter gathered, it left behind a corresponding absence. This process created a vast, 3-dimensional sponge where the solid threads are the filaments, the holes are the voids, and the dense intersections where threads meet become the future homes of galaxy clusters. This sponge-like structure, this cosmic web, was the inevitable result of gravity tracing over the magnified blueprint of the quantum dawn. It was a universe organizing itself, finding order not through design, but through the simple, unstoppable physics of attraction and flow. The grand intersections of the cosmic web are where the story turns from architecture to spectacle. These are the nodes, the gravitational crossroads where multiple filaments converge. Picture the most vital transportation hub in a vast nation, where every major highway, rail line, and shipping route meets. That is the role of a cosmic node, but on a scale where the highways are rivers of dark matter millions of light years long. Here, the combined gravitational pull from all those converging filaments creates an immense, deep well in the fabric of spacetime. It is a place of ultimate gathering, a sinkhole for matter on a cosmic scale. Everything flowing along the filaments, all the dark matter scaffolding and the ordinary matter riding along with it, is funneled relentlessly toward these central points. The result is the formation of the most massive, gravitationally bound structures in the entire universe, galaxy clusters and superclusters. Within these dense metropolitan hubs, thousands of galaxies swarm in a frenetic, chaotic dance. The environment is nothing like the serene spiral we see from our own galactic neighborhood. Here, galaxies are packed so tightly that their mutual gravity constantly tugs and distorts them. They whiz past one another at incredible speeds, often on collision courses that unfold over hundreds of millions of years. These are not destructive crashes in the way we might imagine, but spectacular mergers. When two large galaxies are drawn together, their stars, vast in number but tiny in scale relative to the distances between them, rarely actually collide. Instead, their gravitational fields intertwine, pulling long, streaming tails of stars out into space, and eventually settling into a single, new, often elliptical galaxy. This process is a fundamental engine of galactic evolution, and it happens most frequently in these crowded nodal cities. The sheer density of matter also heats the thin gas between galaxies to incredible temperatures, causing it to glow in X-rays and creating a diffuse, searing atmosphere that permeates the entire cluster. This is the metropolis of the cosmic web, a place of constant construction, demolition, and rebirth, all powered by the relentless inflow from the filamentary highways. While the filaments are the serene, structured rivers of the cosmos, the nodes are the roaring waterfalls where all that gathered potential energy is violently released, forging the universe's most colossal communities. Yet for all the violence of the nodal cities, a quieter, more essential process flows along the filaments themselves. A galaxy is not a static object, it is a living engine of creation, constantly forging new stars from raw material. To keep that engine running, it requires a steady, abundant fuel supply, vast reservoirs of cold gas. This presents a profound mystery. In the early universe, the most massive galaxies we observe formed with astonishing speed, gathering enough material to blaze with the light of billions of stars when the cosmos was still in its youth. How did they acquire so much fuel so quickly? The answer lies not in the chaotic clusters, but in the serene highways that feed them. Scientists call this the cold flow model, and it reveals the cosmic web as the universe's most efficient delivery system. Imagine a vast, primordial forest after a deep winter. The snowpack begins to melt, but instead of forming a wide, shallow lake, the water finds pre-existing gullies in the landscape. It gathers into narrow, fast-moving streams that cut through the terrain, remaining cold and focused as they race downhill. These streams do not evaporate under the sun, they deliver their payload directly to the valley below. This is the essence of cold flow. After the first stars and galaxies began to ignite, they flooded the universe with intense ultraviolet radiation. This radiation had a dramatic effect on the diffuse gas throughout the cosmos, heating it to extremely high temperatures, making it too energetic to easily collapse and form new stars. But within the dense, dark matter filaments of the cosmic web, a different story unfolded. Here, vast rivers of pristine hydrogen and helium gas, the primordial material left over from the Big Bang, continued to flow. Shielded within the deep gravitational troughs of the filaments, this gas could remain remarkably cold and dense. It did not wander randomly through the hot intergalactic medium. Instead, it was channeled. These cold, narrow rivers streamed along the filamentary highways, guided by the same dark matter skeleton that shaped everything. They flowed with purpose, like insulated pipelines spanning hundreds of thousands of light years. Their destination was the growing gravitational wells of young, hungry galaxies situated along the filament or at its end. The gas did not meander and heat up, it plunged directly into the galactic core, a cold, dense infusion of star-making fuel. This model solves the puzzle of the early universe's rapid galactic growth. These proto-galaxies were not left to slowly gather hot, diffuse gas from their surroundings. They were connected directly to the cosmic web supply lines, receiving torrents of cold, ready-to-use material delivered with breathtaking efficiency. Their immense star-forming power was not a mystery of isolated creation, but a consequence of their privileged location within the universe's grand infrastructure. They were cosmic hubs positioned at the terminus of the most productive rivers, and they grew fat on the bounty those rivers carried. This intricate plumbing, established billions of years ago, may have set the course for galactic evolution, determining which galaxies would become titans and which would remain modest. But if the web provides the fuel, what dictates how a galaxy uses it? What internal forces can stifle this flow of creation? And can a galaxy ever truly sever its connection to the web that gave it life? This grand narrative of filaments, voids, and clusters is not just a compelling story. It is a scientific theory, one that makes specific, testable predictions about the structure of our universe. But how do you test a theory about the evolution of everything? You cannot rewind time and run the experiment again. Instead, scientists perform the next best thing. They build a universe inside a machine. Our most profound evidence for the cosmic web comes not only from telescopes, but from some of the most complex calculations ever performed, running on the world's most powerful supercomputers. These are cosmological simulations, and they are our digital laboratories for the cosmos. The process begins with the same starting point we discussed, a nearly uniform soup of matter and energy seeded with those tiny quantum ripples. Scientists program this initial condition into the computer, along with the known laws of physics, primarily the equations of gravity and the behavior of gases under extreme conditions. They then divide this virtual cosmos into billions, even trillions of individual particles. Some represent dark matter, the unseen scaffolding. Others represent the ordinary, baryonic matter that will become stars and galaxies. The supercomputer's task is monumental. It must calculate the gravitational pull between every single one of these particles as they move through an expanding space over the entire 13.8 billion year history of the universe. This requires staggering computational power, running for months on machines that rank among the fastest on Earth. The result is not a pre-drawn animation. It is a genuine emergence. As the simulation runs forward in digital time, something remarkable happens. Without any programmer drawing them in, structures begin to form. The dark matter particles, driven solely by gravity, first coalesce into a delicate cosmic cobweb. Then, the gas follows this dark skeleton, flowing along the filaments, pooling at the nodes, and leaving vast empty voids in between. Galaxies ignite within these dense regions, growing, merging, and evolving just as our telescopes observe. Projects like IllustrisTNG and Eagle have produced these breathtaking virtual universes. When you compare a slice of one of these simulations to a map of the real universe constructed from galaxy surveys, the resemblance is uncanny. The same sponge-like architecture, the same statistical distribution of clusters and voids emerges spontaneously from the math. This is a powerful validation. It tells us that our understanding of the basic physics, from the quantum seeds to the force of gravity, is fundamentally correct. These simulations do more than just recreate what we see. They allow us to ask what if. What if dark matter behaved slightly differently? What if the strength of gravity changed over cosmic time? By altering the initial rules and running the simulation again, scientists can see which set of laws produces a universe that looks exactly like our own. In this way, the cosmic web has become a precision tool. It is the largest possible particle accelerator, and its structure, mirrored in our supercomputers, is confirming the very bedrock of modern cosmology. But how can we be sure this digital mirror is not just a clever illusion? To find the ultimate validation, we must look back to the very beginning, to a photograph taken when the cosmos was just an infant. This is not a metaphor. We possess a literal snapshot of the universe at the tender age of 380,000 years. It is the cosmic microwave background, a faint glow of radiation that fills every direction of the sky. This afterglow is the oldest light in existence, released when the hot, dense plasma of the early universe finally cooled enough for atoms to form, allowing light to travel freely for the first time. That moment when the fog cleared was the universe's first photo opportunity. The camera was the cosmos itself, and the film was the fabric of space-time. The image it developed is not uniform. When we examine it with exquisitely sensitive instruments like the Planck satellite, we see a mottled tapestry of incredibly subtle temperature differences. Some patches are a few millionths of a degree warmer, others are slightly cooler. These are not random blemishes. They are the fossilized imprints of those primordial quantum ripples, magnified by inflation. A slightly warmer patch means the plasma there was a tiny bit denser, a gravitational hill in the making. A cooler patch marks a shallower valley. This pattern is the universe's birth certificate, and it contains the complete genetic code for everything that would follow. Cosmologists have learned to read this code. By applying the laws of physics to these minute fluctuations, they can run the clock forward. They can calculate with mathematical precision how those specific hills and valleys should evolve over 13.8 billion years under the influence of gravity and dark matter. The prediction is clear and specific. Those seeds should grow into a vast, sponge-like cosmic web, with filaments and voids distributed in a very particular statistical pattern. Then we point our telescopes at the real, modern universe. We create three-dimensional maps from galaxy surveys, painstakingly plotting the positions of millions of galaxies. When we compare the actual, observed web to the one predicted from the infant universe's baby picture, the agreement is nothing short of breathtaking. The statistical fingerprints match, the distribution of clusters, the sizes of voids, the threading of filaments. It all aligns with the prophecy written in that ancient light. This is not a vague resemblance. It is a precise, quantitative confirmation that our story, from quantum whisper to cosmic web, is fundamentally correct. The universe left us a message in its first light, and we have finally learned to read it, finding our entire cosmic history written there in a language of heat and shadow. This ancient light reveals a universe built with astonishing consistency, yet within that grand design, individual galaxies hold a secret of their own. If you could stand on the edge of a cosmic filament and look along its length, you might notice something peculiar about the galaxies strung along it. They are not oriented at random like leaves scattered on a pond. Instead, many of them seem to know which way the road is pointing. Their vast spinning disks or elongated shapes show a distinct preference, aligning themselves either parallel to the filament, like a ship sailing with the current, or perpendicular to it, like a log bridging a stream. This subtle but persistent pattern is one of the most fascinating clues embedded in the cosmic web, a fossil memory of how each galaxy was born. Think of a galaxy's spin, its angular momentum, as a kind of cosmic fingerprint. It is a unique signature of all the forces that acted upon the galaxy's raw material as it was assembling billions of years ago. For a long time, astronomers believed this spin was generated by local, chaotic events like mergers with smaller galaxies. But the alignment of galaxies with filaments suggests a far grander, more orderly origin story. The source of a galaxy's spin may not be its chaotic neighborhood, but the immense, structured flow of the entire cosmic web around it. To understand this, picture a vast, slow-moving river of dark matter and gas, a filament hundreds of thousands of light-years across. Now, imagine a young proto-galaxy forming within that river. It is not sitting in still water. The material is flowing past it toward the denser node at the end of the line. This flow creates immense tidal forces, a gravitational stretching effect. It is similar to how the moon's gravity pulls on Earth's oceans, creating a bulge. The flowing cosmic material tugs on the gathering galaxy from specific directions. As the cold streams of gas we discussed earlier funnel into the growing galaxy, they do not arrive from all sides equally. They come channeled along the filament, delivering not just mass, but also a specific sense of rotation, a preferred axis of spin. If the gas flows in along a smooth, direct path, it can set the galaxy spinning like a top, with its axis perpendicular to the filament. In other cases, more complex flows can align the galaxy's shape parallel to the cosmic thread. This means a galaxy's very identity, whether it becomes a majestic, flat spiral or a rounder elliptical shape, may be imprinted upon it by the architecture of the web it grew within. The most massive elliptical galaxies, those titans found at the crowded intersections of filaments, show this alignment most strongly. They are the ultimate products of the web's gravitational delivery system, having consumed vast amounts of material flowing along multiple filaments. Their alignment is a lasting testament to that orderly influx, a final orientation locked in after eons of growth. It is as if each of these galaxies carries within its stars a silent memory, a gravitational echo of the specific cosmic highway that built it. They do not just live in the web, they are physical records of its construction process, their orientations serving as ancient signposts pointing back to the flows that shaped them. This realization deepens our connection to the large-scale universe. It suggests that the forces which sculpt the largest structures also write the blueprint for the smallest details of the galaxies within them, linking the fate of a single star system to the flow of the entire cosmos. But not every galaxy is destined for the crowded metropolis or the flowing highway. In the vast, empty spaces between the threads of the cosmic web, another kind of existence unfolds. These are the cosmic voids, unimaginably immense regions of space that can span hundreds of millions of light-years. To call them empty is not quite right, but they are so desperately sparse that they contain perhaps only 1% of the average matter density of the universe. Within these profound deserts, far from the gravitational pull of any filament or cluster, lie the loneliest galaxies in existence. Astronomers call them void galaxies, and they are the isolated outposts of the cosmos. While their cousins in the dense clusters are shaped by constant gravitational harassment and spectacular mergers, void galaxies experience a universe of profound quiet. They drift in near-total isolation, with perhaps only one or two other galactic neighbors visible across a gulf of emptiness that would take light tens of millions of years to cross. This radical difference in environment leaves a clear signature on the galaxies themselves. Freed from the violent tides and collisions of the crowded web, void galaxies often retain a more primitive, irregular structure. They are frequently smaller, taking on odd, blobby shapes rather than the majestic spirals or smooth ellipses we associate with more social galaxies. More strikingly, they tend to glow with a younger, bluer light. This is the key clue. The blue light comes from massive, hot, young stars. In the voids, the pristine reservoirs of cold gas that fueled a galaxy's birth are not stripped away by passing neighbors or heated by the intense radiation of a cluster. This gas remains available, allowing these isolated islands to continue forming new stars at a gentle, steady pace long after galaxies in denser regions have exhausted their fuel and aged into redder, older stellar populations. In essence, a void galaxy is like a secluded village that has preserved its ancient traditions, untouched by the wars and trade of the bustling empires. Its evolution is not driven by the dramatic, external forces of the cosmic web, but by its own internal, slower rhythms. This makes void galaxies priceless to astronomers. They act as cosmic control subjects. By comparing a void galaxy to a similar-sized galaxy in a cluster, scientists can isolate the pure effects of environment. They can ask what happens to a galaxy when it is left entirely alone. The answer helps us disentangle the story of any galaxy's life, revealing which traits are innate and which are sculpted by the relentless gravitational currents of the web. These lonely outposts remind us that the universe offers many paths. While the grand narrative is written in the flowing filaments and dense nodes, a quieter, more solitary story is being told in the deep, dark spaces between. Yet the cosmic web we observe today is not the same as the one that first emerged from the primordial glow. It is a living structure, a dynamic entity that has been growing, shifting, and maturing for over 13 billion years. In its youth, the universe was a more uniform place. The gravitational blueprint was there, but its features were subtle. The web was a delicate, fine-grained lace, with countless tiny dark matter clumps and thin, wispy filaments stretching across a cosmos that had not yet fully decided its shape. The transformation from that early lace to the bold, sponge-like architecture we see now is the story of gravity's patient, relentless ambition. This process has a name: hierarchical structure formation, and it is the universe's way of building itself from the bottom up. It began with the smallest pieces. Those initial quantum ripples created a spectrum of over-dense regions, some slightly larger, some smaller. Gravity acted fastest on the smallest, densest clumps, causing them to collapse first. These became the building blocks, the cosmic bricks. They did not remain isolated. Drawn together by their mutual attraction, these small clumps began to merge. Two would find each other and become one larger clump. That larger clump would then attract and absorb its neighbors, growing steadily. It is a cosmic game of consolidation, where small villages merge into towns, towns into cities, and cities into vast metropolitan clusters. This merging did not happen in empty space. The dark matter filaments that connected these growing clumps acted as conduits. As matter drained from the surrounding regions into these filaments, they themselves grew thicker and more defined. Imagine a network of tiny streams after a continent-wide rainfall. At first, they are faint trickles across the landscape, but as more and more water is channeled into them from the surrounding soil, they carve deeper channels, becoming creeks, then rivers. The cosmic web undergoes a similar sculpting. The voids, those initial slightly under-dense regions, are the source of this material. Over billions of years, gravity has been slowly but surely evacuating them. The sparse matter that once resided in these cosmic deserts has been steadily pulled outward, siphoned into the waiting filaments and nodes that border the void. This is why the voids we see today are so astonishingly empty. They are not just places where nothing formed, they are places that have been actively cleared out. The web feeds on the voids, growing more pronounced as the deserts expand. The result is a universe growing more extreme with time. The rich get richer and the empty become more desolate. The delicate lace of the early cosmos has coarsened into a stark, magnificent tapestry of dense walls and cavernous gaps, and this evolution is far from over. In the far future, gravity's work will continue unabated. Filaments will thicken further, pulling in the last vestiges of matter from the deepening voids. Isolated galaxy groups along the threads will finally complete their long journey, merging into the colossal clusters at the intersections. The web will become ever more defined, its contrast sharper, until the universe is a collection of isolated superclusters separated by voids of truly unimaginable scale. We are witnessing the cosmic web in its vibrant middle age, a structure still actively writing the next chapter of its own story. This dynamic evolution of the web provides the perfect canvas for one of cosmology's most precise measuring tools. To understand the true scale of the cosmos, we need a ruler. But how do you craft a ruler that spans hundreds of millions of light years? The universe, in its first fiery moments, forged one for us. The secret lies in a phenomenon with a complex name, Baryonic acoustic oscillations, but a beautifully simple origin story. They are the fossilized echoes of sound waves that raced through the newborn cosmos. In that first hot plasma, ordinary matter, the baryons, and light were locked in a fierce struggle. Gravity tried to pull matter into the dense seeds left by inflation, but the intense pressure of radiation fought back, pushing outward. This created a series of pressure waves, like ripples from a stone dropped in a pond, that expanded outward from every over-dense region. These were genuine sound waves, traveling at over half the speed of light through the primordial soup. For about 380,000 years, these waves propagated until the universe cooled enough for atoms to form. In that moment, the music stopped. Light decoupled from matter and streamed freely, creating the cosmic microwave background we see today, but the matter was left behind, frozen in place. Each wave had pushed a spherical shell of matter outward from its origin point, like a bubble expanding and then suddenly solidifying. The radius of that bubble, the distance the sound wave could travel before the music stopped, became a fixed scale in the cosmos, about 500 million light-years across. This left a subtle, regular pattern imprinted on the distribution of matter. It meant that galaxies were slightly more likely to be found separated by this specific distance, or multiples of it, than by any other random spacing. It is as if the universe was stamped with a faint, three-dimensional grid of preferred scales. For billions of years, this pattern was hidden within the chaotic growth of the cosmic web, stretched and distorted by gravity's pull. Yet, like a watermark in fine paper, it remained. Modern galaxy surveys, which map the positions of millions of galaxies, have the statistical power to reveal it. By analyzing the immense three-dimensional maps of the cosmic web, astronomers can detect this faint, preferred separation between galaxy pairs. They are not looking at individual galaxies, but at the statistical heartbeat of the entire structure. And this is where the cosmic web becomes more than architecture. It becomes a measurement device. That 500 million light-year scale is our standard ruler. We know its true size from our understanding of the early universe's physics. By observing how large this ruler appears to us at different distances, and thus at different times in cosmic history, we can measure how space itself has stretched over the eons. If the universe's geometry is flat, as our best models suggest, the ruler will appear one size. If space is curved, it would appear differently. The measurements from the Baryonic acoustic oscillations consistently confirm a flat geometry and precisely chart the accelerating expansion driven by dark energy. It is a profound use of the cosmic web, turning the largest structure we know into the most precise instrument we have for weighing the fate of everything. Yet even with this grand map, a fundamental piece of the cosmic puzzle has remained stubbornly absent. When astronomers tally up all the ordinary matter in the universe, the protons and neutrons that compose every star, planet, and living thing, they come up short. A staggering amount, perhaps as much as half of all the normal matter predicted to exist from the Big Bang, simply cannot be found. This is the missing Baryon problem, a cosmic accounting error on the largest possible scale. We see the luminous galaxies and the hot gas in clusters, but their combined mass is only a fraction of what our models say should be there. Where has the rest of the universe's building blocks gone? The prime suspect is not some exotic new particle, but a form of matter so diffuse and elusive it has slipped through our observational nets for decades. It is believed to be hiding in plain sight, woven directly into the fabric of the cosmic web itself. This is the warm-hot intergalactic medium, or WIM. Picture the vast filaments not as solid threads, but as immense, ghostly conduits filled with a superheated gas. This gas is not cold and dense like the material that forms stars. It has been shock-heated to temperatures of millions of degrees by the violent gravitational forces that sculpted the web. At such extreme heat, the gas is ionized, meaning its electrons have been stripped from their atoms. This makes it incredibly thin and faint. It does not glow with the characteristic light of cool hydrogen, the signature astronomers typically search for. Instead, it is a nearly invisible fog, a tenuous plasma that permeates the spaces between the galaxies strung along the filaments. Detecting it is one of the greatest observational challenges in modern cosmology. It is like trying to see the heat haze rising from a desert highway from thousands of miles away. the whim reveals itself only through the most subtle of clues. When the brilliant light from a distant quasar passes through one of these hot filaments, the highly ionized atoms within the gas can absorb specific, very high energy wavelengths of that light, particularly in the far ultraviolet and soft X-ray parts of the spectrum. Finding these faint absorption lines is a painstaking task, requiring space-based telescopes and immense patience. Each detection is like catching a single, whispered word from a conversation happening across the universe. But slowly, by combining thousands of these quasar sightlines, a picture is emerging. The missing baryons appear to be there, exactly where the theory of the cosmic web predicted they would be, dissolved into the vast, hot atmosphere of the filaments. Completing this census is about more than just balancing the cosmic books. It is about verifying our entire understanding of how structure forms. If we can finally map this warm, hot intergalactic medium in detail, we will be seeing the final component of the universe's ordinary matter, the last traces of the primordial gas that never made it into a star or a galaxy. It is the backdrop against which the luminous universe is painted, the hidden sea in which all islands of light ultimately float. This search for the universe's missing material requires a new way of seeing, a method that can peer into the searing heat of the cosmic web's hidden rivers. One of the most powerful techniques does not look for the gas itself, but for the subtle shadow it casts upon the oldest light in the cosmos. It is called the Sunyaev-Zeldovich Effect, and it transforms the cosmic microwave background from a baby picture into an immense cosmic X-ray film. Here is how it works. That ancient afterglow from the infant universe is still washing over everything, a nearly uniform bath of microwave radiation. But when this pristine light journeys across the cosmos on its way to our telescopes, its path is not always clear. If it passes through a vast cloud of hot, ionized gas, like the million-degree plasma in a galaxy cluster or a filament, something remarkable happens. The fast-moving electrons in that superheated gas collide with the microwave photons. It is not a destructive crash, but a glancing blow, like a cue ball striking another on a pool table. In these interactions, the photons gain a tiny amount of energy from the electrons. This minuscule boost shifts the photons very slightly from the colder, microwave part of the spectrum toward slightly higher energies. The result is not a bright flash, but a specific, subtle distortion in the map of the cosmic microwave background. In the precise location of that hot gas cloud, the ancient light appears ever so slightly dimmer at its original, colder frequency and brighter at a slightly warmer one. It creates a faint, shadowy imprint, a cosmic silhouette. For decades, this was a theoretical prediction. But with the advent of exquisitely sensitive radio and microwave telescopes, like the Planck satellite and the Atacama Cosmology telescope, it has become a revolutionary observational tool. These instruments scan the entire sky, not looking for galaxies, but meticulously measuring the temperature of the cosmic microwave background in every direction. Their data reveals a sky peppered with these subtle SZ shadows. Each one is a signpost marking a massive reservoir of hot gas. The largest and most distinct shadows correspond to the enormous galaxy clusters, where the gas is densest and hottest. But the real prize lies in the fainter, more extended signals. These could be the whispers of the warm, hot intergalactic medium itself, the hot gas stretched along the vast filaments of the cosmic web. By meticulously mapping the pattern and strength of these distortions across the sky, astronomers are constructing a new kind of chart. It is a map drawn not in starlight, but in the absence of it, a negative image of the universe's hottest, most diffuse material. This SZ survey acts as a massive fishing net, trawling the cosmos for the elusive baryonic matter that has evaded every other search. Every faint shadow it catches is another piece of the puzzle, helping to confirm that the missing building blocks of the universe are indeed hiding in the immense, heated corridors between the galaxies, exactly as the grand theory of the cosmic web has long suggested. The universe's grand design is not a permanent fixture. It is a temporary masterpiece, a structure born from a delicate balance of forces that will not last forever. That balance is now shifting, and the architect of its eventual dissolution is dark energy. This mysterious form of energy, woven into the fabric of space itself, is causing the expansion of the universe to accelerate. For billions of years, gravity has been the dominant force shaping the cosmic web, pulling matter together into its magnificent filaments and nodes. But dark energy acts as a counterforce, a kind of anti-gravity that pushes space apart. Right now, on the scales of galaxy clusters and the web itself, gravity is still winning locally. Yet on the largest scales, the tide is turning. As the acceleration continues, it will begin to fundamentally rewrite the fate of everything we see. The first signs of this future are already written into the light of distant supernova and the stretching of our cosmic ruler, telling us this is not a speculation, but an inevitable trajectory written into the laws of physics. The era of construction is giving way to an era of isolation. Consider the great filaments, those flowing rivers of galaxies and gas. Their existence depends on a dynamic tension. Gravity pulls material along them toward the dense clusters, while the overall expansion of space gently resists that flow. In the far future, as dark energy's push becomes overwhelmingly strong, that resistance will harden into an impenetrable barrier. The expansion of space between structures will become so rapid that it will surpass even the speed of light relative to distant points. This does not violate Einstein's laws, as it is space itself stretching faster than light can travel through it. The consequence is profound. The flow of cold gas along the filaments, the very fuel line for star formation, will be severed. A galaxy waiting for a new delivery of pristine hydrogen will wait forever, as the river bringing it simply evaporates into the widening gulf. The filaments themselves will not snap, but they will stretch, thin, and fade. They will become ghostly outlines, their constituent galaxies freezing in place relative to one another, no longer able to move along the gravitational highway as the road itself is stretched to infinity. The dense metropolitan hubs, the galaxy clusters, will face a different but equally final fate. Within these giant knots, gravity's grip is so powerful that dark energy cannot tear them apart internally. Their local bonds are too strong, so they will undergo a kind of internal consolidation. All the galaxies swirling within a cluster will, over trillions of years, eventually merge through slow, inevitable collisions. Imagine a dance hall where the music gradually slows and stops. The dancers, no longer whirling, gently drift together and embrace. The result will be a single, monstrously large elliptical galaxy at the heart of each former cluster, a behemoth containing the combined starlight of thousands of merged galaxies. This giant will blaze with the light of aging stars, a final, brilliant monument to the cluster's past activity, but it will be an island. The cluster, once fed by filaments from all directions, will find itself cut off. All the threads connecting it to the rest of the cosmic web will have stretched beyond the horizon of visibility. From the perspective of this super-galaxy, the rest of the universe will have simply disappeared. The observable universe will shrink to the boundaries of its own gravitational prison. This leads to the loneliest possible outcome. Trillions upon trillions of years from now, the cosmos will be a collection of these isolated island universes, each one a darkening giant adrift in an infinite, ever colder void. The magnificent sponge structure of the cosmic web, having been pulled apart, will be replaced by a featureless, expanding emptiness punctuated by rare, fading points of light. Within each island, star formation will have long since ceased as the last reserves of gas are exhausted or locked away in stellar remnants. The stars themselves will burn out, from the brilliant blue giants to the long-lived red dwarfs, until only the faint, cold embers of white dwarfs and neutron stars remain. The universe will enter an age of darkness and profound quiet, a state cosmologists call heat death, where energy is uniformly distributed and no work can be done. It is a poetic and somber conclusion, the same quantum whispers that seeded all of creation, magnified by inflation and sculpted by gravity into a billion light-year tapestry, will see their handiwork erased by the silent, relentless push of dark energy. The story of the cosmic web, therefore, is not one of eternal order, but of a beautiful, transient architecture, a fleeting moment of magnificent structure in the vast, unfolding timeline of the cosmos. Yet this entire majestic story rests upon a profound assumption that our understanding of gravity is complete. What if the invisible architect is not a form of matter we cannot see, but a subtle flaw in the laws of physics themselves? This is the bold question posed by alternative theories like modified Newtonian dynamics or MUND. Its premise is elegantly simple. Perhaps there is no dark matter at all. Instead, the strange motions of stars within galaxies and the behavior of galaxy clusters could be explained by a tweak to how gravity operates over vast distances. In this view, Isaac Newton's famous law and even Einstein's theory of general relativity might be close approximations that break down in the extreme weak gravity environments found in the outer reaches of galaxies and the deep voids of space. Proponents suggest that gravity could become slightly stronger in these regimes, providing the extra pull needed to hold fast-spinning galaxies together without invoking an unseen substance. It is a compelling idea, a kind of cosmic Occam's razor that seeks to solve multiple mysteries by refining a single, fundamental force rather than inventing a new form of matter that has never been directly detected in a lab. For individual galaxies, especially isolated ones, MUND can be remarkably successful at predicting their rotation without dark matter. But the cosmic web presents a monumental, perhaps insurmountable, challenge for such modifications. The standard model with dark matter does not just explain one galaxy. It builds an entire universe from the quantum seeds up. It predicts with stunning accuracy the specific statistical patterns we see in the cosmic microwave background, the precise clustering of galaxies, the distribution of filaments and voids, and the very existence of the web's large-scale architecture. For a modified gravity theory to be a true alternative, it must do the same. It must start with those same quantum ripples in the early universe and, using its revised equations, show how they grow over 13.8 billion years into the exact sponge-like cosmos we observe. So far, no version of MUND has been able to pass this comprehensive test. While it can address certain galactic behaviors, replicating the full, rich tapestry of the cosmic web, the detailed maps from galaxy surveys, the specific temperature fluctuations in the ancient light, the existence of massive, hot galaxy clusters has proven extraordinarily difficult. The intricate ballet of structure formation seems to require the invisible, clustering scaffolding of dark matter to set the stage and guide the actors. Without it, simulations struggle to produce a universe that looks anything like our own. This does not mean the quest is over. Science thrives on such challenges, on the tension between a dominant theory and its rivals. The investigation into modified gravity pushes our understanding to its limits, forcing us to check and recheck every assumption in the standard model. Yet for now, when it comes to explaining the origin and evolution of the largest structure in existence, dark matter remains the most successful blueprint we have. It is the framework that best accounts for the magnificent billion-light-year web we find ourselves woven into, a silent partner in gravity's grand construction project. Mapping the universe's largest structure is a task of impossible scale for any single research team. It demands analyzing the shapes, colors, and positions of millions upon millions of galaxies, a process that would take centuries for even the most advanced automated systems working alone. But in the last 2 decades, a quiet revolution has unfolded, one that connects the curiosity of people around the world directly to the frontiers of cosmology. This is the power of citizen science, where the collective pattern recognition of the human eye becomes a vital tool for discovery. Projects like Galaxies have transformed this monumental challenge into a shared human endeavor. The premise is beautifully simple. Astronomers upload thousands of raw, unprocessed images from robotic sky surveys to a public website. Volunteers, from students to retirees, are then presented with a single, stunning image of a distant galaxy. They are asked a series of straightforward questions. Does it have a spiral structure? Is it smooth and round? Does it show signs of a merger or a distinct bar across its center? With a few clicks, anyone can contribute a classification, adding one day to point to a growing global census. What emerges from this collective effort is extraordinary. While a computer algorithm might struggle with the messy, varied shapes of real galaxies, the human brain excels at it. We instinctively recognize the delicate arms of a spiral, the fuzzy blob of an elliptical, or the chaotic wreckage of a collision. Each volunteer classification is a tiny piece of a puzzle, but when you combine hundreds of thousands of people making millions of classifications, you get something powerful, a statistically robust map of galaxy types across vast swaths of the cosmos. This human-powered data is gold for researchers studying the cosmic web. By knowing not just where a galaxy is, but what kind of galaxy it is, scientists can begin to paint a much richer picture of its environment. They can ask, do the serene spiral galaxies, which need calm conditions to maintain their delicate disks, tend to live in the quieter stretches along filaments, away from the chaotic nodes? Do the giant, round elliptical galaxies, often the products of violent mergers, cluster overwhelmingly at the dense intersections of the web? The answers provided by citizen scientists help validate and refine our models of how environment shapes galactic destiny. Every click by a volunteer is more than just sorting an image. It is placing a single stitch in the grand tapestry of the cosmic web. It is a direct collaboration between public curiosity and professional science, proving that the desire to understand our place in the universe is a shared human trait, and that sometimes the most advanced tool for mapping the cosmos is the collective power of our own perception. Our very existence may be a product of cosmic geography. The grand architecture of the cosmic web does more than just arrange galaxies. It creates a spectrum of neighborhoods, each with wildly different conditions for life. We find ourselves in the Milky Way, a magnificent spiral galaxy that is not floating in isolation, nor is it trapped in a dense urban core. We are part of a modest gathering called the Local Group, which includes our galaxy, Andromeda, and several dozen smaller companions. Crucially, our entire group is situated along a relatively quiet filament, a spur line feeding into the much larger Virgo supercluster. This places us in a cosmic suburb, a location that may have been perfectly poised for life to emerge. The violent centers of galaxy clusters are hostile environments for planetary stability. Within those dense metropolitan hubs, the gravitational tides are fierce, constantly wrenching and distorting galactic shapes. Close encounters between galaxies are frequent, disrupting their delicate spiral structures and hurling stars into chaotic orbits. The space between galaxies is also flooded with intense X-ray radiation from superheated gas, a form of cosmic pollution that could sterilize entire planetary systems. In such a turbulent district, the gentle, stable conditions needed for a planet like Earth to orbit its star for billions of years uninterrupted would be exceedingly rare. Our position on a quieter filament, however, offered a gentler path. Here, the Milky Way has experienced a relatively peaceful history. It has had time to settle into its elegant spiral form, with its stars orbiting in orderly fashion. This stability allowed our solar system to form in a calm region of the galactic disk, far from the energetic core. It provided the billions of years of uneventful cosmic weather necessary for life on Earth to evolve from simple single cells into the complex, conscious observers we are today. This line of thinking leads to a profound possibility known as the galactic habitable zone. Just as a star has a region where planets can have liquid water, the cosmic web may define regions where galaxies themselves are most likely to host complex life. The safest real estate might not be in the richest clusters or the loneliest voids, but in the calm, well-connected suburbs along the filaments, close enough to resources for galactic growth, but far enough from the gravitational chaos to allow for planetary serenity. Our address in the universe, therefore, might be more than just a random coordinate. It could be a fundamental prerequisite written into the story of our own origin, a quiet corner in a vast web that made our cosmic moment of awareness possible. The galaxy we see today is a living archive, its current form a direct record of its cosmic upbringing. To understand its story, we must become intergalactic archaeologists, learning to read the clues written not in stone but in starlight and location. Just as the ruins of an ancient city reveal its history through layers of construction, destruction, and trade routes, a galaxy's present state, its shape, its color, its motion, holds the indelible imprint of the environment that shaped it. Its address within the vast cosmic web is the single most telling clue to its past. Consider a galaxy found in the dense, frenetic core of a massive cluster. It is almost certainly a giant elliptical galaxy glowing with a dull red light. This red color is a critical piece of evidence. It signifies a population of ancient, cooler stars with little to no vibrant blue light from new stellar nurseries. Astronomers often call such galaxies red and dead. Their story is one of a dramatic, accelerated youth. Forming early in one of the universe's richest overdensities, this galaxy was born into a crowded metropolis. Its life was shaped by relentless gravitational encounters. It experienced frequent, violent mergers with other large galaxies, events that violently churned its gas, triggering furious but short-lived bursts of star formation that quickly exhausted its fuel reserves. These mergers also destroyed any delicate spiral structure, puffing the galaxy into a smooth, round shape. The intense heat from the cluster's surrounding plasma further stripped away any remaining cool gas, the raw material for new stars. The result is a galactic elder, its star-forming days long over, a monument to a tumultuous past written in its serene, red glow. Now follow a filament out from that dense cluster to a quieter stretch. Here, you are more likely to encounter a majestic spiral galaxy like our own Milky Way. Its brilliant blue spiral arms, traced by clusters of hot, young stars, tell a completely different story. This galaxy experienced a more orderly, isolated evolution. Positioned along a cosmic highway but not at its chaotic terminus, it enjoyed a steady, regulated inflow of cold gas from the filament. This provided a sustained fuel supply for star formation, allowing it to build its disk gradually over billions of years. Safe from the constant gravitational harassment of a cluster core, it could maintain its delicate spiral structure. Its history is one of peaceful accretion and internal rhythms, a long, stable chapter in the cosmic storybook, resulting in a galaxy still vibrant with ongoing creation. This forensic approach extends to the loneliest outposts of all, the cosmic voids. The few, small, irregular galaxies found drifting in these immense deserts are the cosmic equivalents of isolated mountain villages. Their odd, blobby shapes and blue hues suggest a history of profound quiet. They have never experienced a major merger. They have held onto their primordial gas, and with little competition or disruption, they have formed stars at their own slow, steady pace for eons. They are living fossils, preserving a mode of galactic life that has largely vanished from the busier districts of the web. By conducting a grand census, by categorizing galaxies by type and cross-referencing them with their precise location in the web. Void, filament, or cluster, node astronomers are piecing together a universal rulebook of galactic evolution. We are learning that a galaxy's destiny is not written solely at its birth, but is profoundly authored by its neighborhood. The cosmic web is more than a map of where things are. It is a chronicle of what happened to them, a narrative of construction and transformation written across the sky itself. This grand narrative of galactic evolution, pieced together from our cosmic senses, faces a profound and humbling limitation. Every map we create of the web is not a snapshot of the present, but a collection of messages from the past, each arriving on a delayed schedule. The speed of light, while unimaginably fast, is not instantaneous. It is a cosmic speed limit with a deep consequence for observers like us. When we point our telescopes at a galaxy 1 billion light-years away, we are not seeing it as it is today. We are seeing it as it was 1 billion years ago, when the light now striking our mirrors began its long journey across the void. This transforms our three-dimensional maps of the cosmic web into something even more remarkable, a four-dimensional atlas of cosmic history. Each layer of distance corresponds to a layer of time. By looking at galaxies at a moderate distance, we see the universe in its adolescence. By peering to the farthest, faintest objects, we gaze back into its childhood. This allows astronomers to perform an extraordinary feat, constructing a time-lapse of the web's evolution. By comparing maps of different cosmic epochs, we can literally watch the universe grow up. In the early, high-redshift universe, the web appears as a delicate, fine lace. The filaments are thinner, more numerous, and the voids are smaller. It is a universe that has not yet fully decided its shape, where the gravitational consolidation is just beginning. As we look at maps from progressively later times, we witness the coarsening of that lace. The filaments thicken as matter drains into them, the voids expand and empty out, and the nodes grow into the monstrous galaxy clusters we see in our local neighborhood. This cosmic time-lapse is our most direct evidence for the theory of hierarchical structure formation, allowing us to confirm the predictions of our simulations with real observational data from across the ages. Yet this incredible gift of a time machine comes with a permanent constraint. We can never see the contemporary, full-scale structure of the entire universe. Our view is confined to what is called our past light cone. Imagine standing in a vast, dark forest with a single, powerful flashlight. You can only see the trees that are illuminated within the beam of your light. You cannot see the forest as it exists in the present moment beyond that cone of illumination. You only see each tree as it was when the light left it, which for more distant trees was longer ago. Our observational situation is precisely that, but on a cosmic scale. We see a slice of cosmic history, a fossilized record of events whose light has had time to reach us. We can map a web that stretches billions of light-years deep, but that map is a mosaic of different eras, not a single moment in time. The grand contemporary architecture of the universe as a whole, the complete and current cosmic web, lies forever beyond our direct view. We are historians of the cosmos, piecing together the story from chapters that arrive out of sequence, forced to infer the present state of the whole from the fragmented, ancient light of its parts. The silent flow of gas along the cosmic web is not the only force shaping its destiny. Deep within the galaxies strung along those filaments, another, far more violent architect is at work. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not inert sinkholes, but dynamic engines of creation and destruction. When they actively feed on the gas funneled in by the cosmic web, they do not consume quietly. The infalling material swirls into a superheated disk, and in a spectacular release of gravitational energy, the black hole can launch jets of particles at nearly the speed of light and flood its host galaxy with intense radiation. This outburst is a form of cosmic feedback, a self-regulating mechanism with consequences that ripple far beyond the galactic core. The energy from these eruptions heats the surrounding reservoirs of cold gas, the very fuel for star formation. In some cases, it drives powerful galactic winds that can blow that gas clear out of the galaxy entirely. Think of it as a galactic thermostat. If a galaxy grows too fast, feasting too greedily on the gas delivered by its filament, the central black hole awakens. Its furious output shuts down the star-forming factories, preventing the galaxy from burning through its fuel too quickly. This feedback ensures a galaxy's growth is sustainable, transforming a potential brief, brilliant flash into a longer, more stable life. But the influence does not stop at the galactic borders. These energetic outflows can be so powerful that they push into the circumgalactic medium, the halo of gas surrounding the galaxy, and even reach into the filament itself. By heating and stirring the gas within the cosmic thread, the black hole's activity can temporarily stifle the flow of fuel to neighboring galaxies or alter the conditions for future star formation along that entire stretch of highway. This creates a profound link across scales. The behavior of an object smaller than our solar system, governed by the extremes of gravity, can dictate the gas dynamics across hundreds of thousands of light years, influencing the evolution of the largest structures in the universe. The cosmic web is not a static sculpture, then, but a living system. It is shaped not only by the grand, external forces of gravity and dark energy, but also by the fierce, internal heartbeats of the galaxies that call it home. The universe's first cities of light emerged from a profound and ancient darkness. When the cosmos was less than 1 billion years old, the first galaxies ignited, their starlight piercing the primordial gloom. Their formation remains one of the great cosmic mysteries. How could such immense structures containing billions of stars assemble with such breathtaking speed in the infancy of everything? The answer is woven into the earliest threads of the cosmic web. In that distant era, the web was not the bold, coarsened tapestry we see today. It was a delicate, ghostly lace, its filaments wispy and its voids relatively small. But the fundamental process was already in motion. The invisible scaffolding of dark matter had traced out the first rivers and intersections, and along these nascent highways flowed the universe's most precious resource, pristine rivers of cold hydrogen and helium gas, untouched by the forge of any previous star. This was the raw, perfect fuel for creation. The theory of cold flow suggests these first galaxies did not slowly gather hot, diffuse gas from a chaotic void. Instead, they were born at the termini of these cosmic supply lines. Picture a seedling at the end of an underground spring, receiving a direct cold infusion of water that allows it to grow with astonishing vigor. The first galaxies were those seedlings, positioned at the gravitational sinks where multiple thin filaments converged. The cold gas, channeled and focused by the dark matter skeleton, streamed directly into their cores, collapsing rapidly into the first generations of brilliant, massive stars. This efficient, targeted delivery system could explain the puzzle of their rapid and prolific growth. They were not struggling to build themselves from scattered scraps. They were fed by the universe's first and most productive infrastructure. Yet observing this foundational epoch pushes our technology to the absolute limit. The light from these infant galaxies has traveled for over 13 billion years to reach us. In that unimaginable journey, the expansion of the universe has stretched their once visible light far into the infrared part of the spectrum, a faint, redshifted whisper. Our current telescopes strain to hear it. This is where a new era of discovery is poised to begin. Instruments like the James Webb Space Telescope are engineered specifically for this task. With its giant, gold-coated mirror and exquisitely sensitive infrared instruments, it is a time machine designed to peer into the cosmic dawn. Its mission is to catch the first galaxies not as mature systems, but in the very act of assembly. Scientists hope to see them as small, blue, chaotic knots of intense star formation, strung along the faint, glowing traces of hydrogen gas that outline the infant web itself. By mapping these first lights and the gas that connects them, we may finally witness the moment the cosmic web transitioned from a silent blueprint in dark matter to a luminous reality, watching as the universe lit its first lamps along the invisible roads it had built for itself. But this grand cosmic map is far more than a beautiful portrait. It is a time machine and a laboratory combined. The intricate pattern of filaments and voids we observe today is not a random accident. It is the final, frozen result of a 13.8 billion year-long physics experiment, one that began with the quantum ripples of inflation. Every subtle detail in this vast structure, the precise spacing of galaxy clusters, the characteristic thickness of the filaments, the staggering emptiness of the voids, all of these features depend on the exact laws and ingredients that have governed the universe since its birth. This means that by meticulously measuring the cosmic web, we are conducting a direct test of the most fundamental rules of reality. The web's architecture is exquisitely sensitive to the properties of the universe's most mysterious components. Take dark matter, for instance. If dark matter particles were warm, meaning they moved at significant fractions of light speed in the early universe, they would have smoothed out the smallest cosmic structures. We would see a web with fewer fine, wispy filaments and smaller dwarf galaxies. The fact that we observe such a rich, fine-grained tapestry strongly suggests dark matter is cold, moving slowly and clumping easily from the very beginning. The web also feels the subtle push of dark energy. The accelerating expansion it causes stretches the distances between structures, affecting how matter flows along the filaments and how empty the voids become over time. By measuring the web's evolution across cosmic epochs, we can precisely weigh the strength and nature of this mysterious energy. Even the tiny, nearly massless neutrino, a ghostly particle that floods the cosmos, leaves a fingerprint. Because neutrinos rarely interact and stream almost freely, they act like a cosmic pressure, resisting gravity's pull on the smallest scales. Their collective mass, however small, subtly suppresses the formation of the very faintest filaments and tiniest galaxies. By mapping the cosmic web with incredible precision, we can, in effect, weigh the neutrino. This turns the entire observable universe into the most sensitive scale imaginable. To perform these tests, scientists are building a new generation of cosmic cartographers. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are creating maps of unprecedented scale and detail. Mounted on a telescope in Arizona, DESI is not taking pretty pictures. Instead, it uses 5,000 robotic fibers to capture the light of tens of millions of galaxies and quasars, measuring their distances to construct a three-dimensional chart of the universe spanning 11 billion years of cosmic history. Each point on this map is a data point in the grand experiment. By comparing this immense, real-world structure to the predictions of supercomputer simulations that use different physics, different dark matter properties, or different dark energy strengths, we can see which theoretical universe matches our own. It is a process of elimination on the grandest possible scale. We are not just looking at the cosmos, we are interrogating it. The silent, sprawling web of galaxies has become our most powerful tool for answering questions that no particle accelerator on Earth could ever touch, revealing the hidden laws that have written the story of everything. There is a breathtaking elegance to the universe's grand design, a beauty that transcends the cold mathematics of its creation. The cosmic web, in its final form, is not merely a structure, it is a masterpiece of natural geometry. Its branching filaments and cavernous voids possess a haunting, fractal-like quality, where patterns repeat on ever larger scales, from the local tendrils connecting galaxy groups to the billion light-year walls defining superclusters. This intrinsic aesthetic has forged a unique bridge between two seemingly distant worlds, the rigorous realm of astrophysics and the expressive domain of art. The visualizations born from supercomputer simulations are far more than diagnostic tools for researchers. They are profound portraits of reality, digital frescoes painted with algorithms and data. When scientists render the results of a project like IllustrisTNG, they make deliberate artistic choices, color-coding dark matter density, gas temperature, or star formation rates to create images and animations of staggering depth and drama. These are not artists' impressions, they are translations of physical law into visible form, and what they reveal is a universe of unexpected and majestic artistry. This collaboration between code and canvas serves a vital purpose for all of us. The raw data of cosmology, the tables of redshifts and spectra, remain abstract and inaccessible. But a visualization, a swirling flight through a synthetic universe where galaxies bead along glowing amber threads against an infinite black velvet, communicates directly to our sense of wonder. It allows the human mind, which evolved to navigate a forest, to intuitively grasp the architecture of a cosmos. It transforms an intellectual concept into an emotional experience, fostering a deep, visceral connection to a reality we can never visit. In this way, the scientific pursuit of the cosmic web does more than satisfy our curiosity. It returns to us a gift of perspective and profound beauty. It reminds us that the drive to understand the universe is not separate from the drive to appreciate its splendor. The same fundamental laws that govern the collapse of a gas cloud into a star also sculpt the largest possible structure into a form that resonates with our innate sense of pattern and harmony. The web shows us that truth and beauty, science and art, are not opposing forces, but complementary ways of witnessing the same magnificent story written across the sky. The vast emptiness is not an afterthought, but a fundamental feature of the cosmic design. These cosmic voids, spanning hundreds of millions of light years, comprise the overwhelming majority of the universe's volume. Their profound emptiness presents a deep puzzle. Why would a cosmos born from a nearly uniform sea of energy choose to arrange itself into such staggering deserts, leaving its luminous matter gathered in mere threads and knots? The answer is written into the original statistics of those quantum whispers. The primordial fluctuations were not perfectly uniform hills, they were a spectrum of peaks and valleys. For every slightly denser region destined to become a galaxy cluster, there was a corresponding region of slightly lower density. In the great gravitational sorting that followed, this was a zero-sum game. As matter drained into the peaks flowing along the filaments toward the nodes, it had to come from somewhere. That somewhere was these initial valleys. The voids are not places where nothing happened. They are places that were actively evacuated over billions of years. They are the natural, necessary counterpart to the dense structures, the negative space that defines the positive image of the web. This makes them not cosmic dead zones, but laboratories of exceptional power. While galaxy clusters show us gravity's might in crowded, complex environments, the voids show us the pure, unopposed force of cosmic expansion. With so little matter inside to provide gravitational resistance, the stretching of space itself is the dominant actor. The growth, shape, and evolution of a void are exquisitely sensitive to the push of dark energy. Think of a void as a bubble in an expanding loaf of bread. The dough itself, representing space-time, is rising. If the yeast is weak, the bubble grows slowly. If the yeast is strong and the expansion accelerates, the bubble inflates more rapidly, its walls stretching and thinning. By measuring the shapes and sizes of voids across cosmic time, astronomers can take the universe's temperature, gauging the precise strength of dark energy's influence. Even the tiny amount of matter left behind in a void, often just a few isolated galaxies, tells a critical story. The way these lone galaxies move or fail to move reveals the void's gravitational profile or lack thereof. They are test particles in a nearly perfect vacuum, their motions tracing the subtle gravitational remnants of the void's evacuation. Studying emptiness, therefore, becomes one of our sharpest tools for understanding the forces that fill the universe. The silence of the void speaks volumes about the energies that shape our reality. This grand narrative connects scales of reality that defy human intuition. It is a story that begins in a realm where the concepts of here and there, or before and after, lose all meaning. In the first fleeting moments, the entire cosmos was governed by quantum uncertainty, a seething foam where particles and energy flickered in and out of existence. Within that foam, random ripples emerged in the underlying quantum fields, fluctuations so minuscule they were utterly insignificant on their own scale. Yet these were the first notes of a symphony that would play for billions of years. The subsequent inflationary expansion acted as a cosmic amplifier of unimaginable power, stretching those quantum whispers across the entire observable universe. What was once a random subatomic event became a macroscopic feature, a subtle hill in the density of the cosmos that spanned millions of light years even before the first atoms formed. This is the first astonishing link in the chain, where the probabilistic rules of the very small were etched onto the canvas of the very large. From that moment, the baton was passed to gravity. This force, which governs the fall of an apple and the orbit of planets, became the universe's primary sculptor. But gravity did not work on the hot, radiant plasma of ordinary matter right away. It first acted upon the unseen dark matter, a substance that feels gravity's pull but not the push of light. This dark scaffolding began to trace out the amplified quantum pattern, gathering in the overdense regions and drawing the first faint outlines of a web. This is where particle physics meets astrophysics, as the nature of the dark matter particle, whether it is cold, warm, or something else, directly determines the texture of the emerging cosmic tapestry. The properties of a hypothetical particle, studied in deep underground laboratories and massive particle colliders, dictate whether filaments are thick or thin, and whether dwarf galaxies are plentiful or rare. As this dark skeleton matured, it set the stage for the final act, the assembly of the luminous universe we see. This is the domain of hydrodynamics, the physics of flowing gases. The ordinary matter, the protons and neutrons that make up stars and planets, was now cool enough to feel gravity's call. It flowed like a cosmic river, channeled by the invisible gravitational troughs of the dark matter filaments. Shock waves rippled through this gas as it crashed into the growing nodes, heating it to millions of degrees. The intricate ballet of cooling, condensation, and collapse within these flows gave birth to the first stars and galaxies. The story thus weaves together the behavior of subatomic particles, the relentless pull of gravity across void, and the complex fluid dynamics of an ionized plasma, all into a single, coherent explanation for why the night sky looks the way it does. This synthesis of disciplines is what makes the cosmic web such a monumental scientific achievement. It is not the domain of any single field. Cosmologists provide the initial conditions from the afterglow of the Big Bang. Particle physicists theorize the nature of the dark matter that forms the web's backbone. Astrophysicists model the violent lives and deaths of stars within the galaxies. Fluid dynamicists simulate the behavior of the hot gas that weaves through it all, and computer scientists build the digital universes that bring these laws together, allowing us to watch the story unfold. The cosmic web stands as a testament to the unifying power of human curiosity, demonstrating that the deepest truths of the universe are not found in isolation, but in the breathtaking connections between every scale of existence, from the quantum foam to the great galactic walls. The coming decade will transform our cosmic charts from detailed sketches into living, breathing atlases, A new generation of observatories, both on the ground and in space, is preparing to launch a golden age of cosmic cartography. Each instrument is designed to see the universe in a different light, and together they will weave a three-dimensional portrait of the web with a precision that feels almost like touching the structure itself. On a mountaintop in Chile, the Vera C. Rubin Observatory will soon begin the legacy survey of space and time. Its enormous mirror and massive camera will scan the entire southern sky every few nights, not just once, but over and over for 10 years. This relentless patrol will detect and measure the brightness of billions of galaxies, tracking subtle changes that reveal their distances. It will find so many galaxies that our current maps will look sparse by comparison, filling in the faintest threads of the web we have only inferred statistically. In space, the Nancy Grace Roman Space Telescope will join this effort with a different, powerful advantage. Free from the shimmering blur of Earth's atmosphere, it will peer into the infrared spectrum with crystal clarity. This allows it to see the stretched light from the most distant galaxies with extraordinary sharpness, mapping the web's architecture deep into the past and watching its evolution across cosmic time with a steady, unwavering gaze. Meanwhile, an immense collaborative effort across two continents will listen to the universe. The Square Kilometre Array, a network of thousands of radio antennas spread across South Africa and Australia, will act as a single giant ear tuned to the cosmos. It will detect the faint radio signature of neutral hydrogen gas, the primary fuel of the universe. This will let astronomers map not just where the galaxies are, but trace the rivers of raw material flowing along the filaments themselves, even the faint, diffuse gas that has eluded us for so long. The combined data from these titanic projects will be staggering. We will move from maps of millions of galaxies to maps of billions. This torrent of information will allow scientists to construct ultra-high-resolution, three-dimensional models of the cosmic web. We will not just see the nodes and filaments, we will be able to trace the velocity of galaxies flowing along them, measure the gravitational tug of dark matter in the emptiest voids, and weigh the warm-hot intergalactic medium with unprecedented accuracy. Within this exquisitely detailed tapestry, we may find subtle distortions, tiny wrinkles in the web's pattern that current models cannot explain. These could be the fingerprints of dark matter particles interacting in unexpected ways, or clues that dark energy's repulsive force has changed strength over the life of the cosmos. The next maps will not just show us the universe's structure, they will let us stress test its very foundations, searching for cracks in our understanding within the silent architecture of everything. The silent architecture surrounding us whispers a profound truth about the nature of reality itself. This cosmic web, a structured and evolving network, is not a chaotic accident. It is the direct and inevitable consequence of a universe that plays by consistent, knowable rules from its very first moment. The immense complexity we see, the billion-light-year tapestry of filaments and voids, did not require a complex blueprint. It emerged from astonishingly simple beginnings, a nearly uniform sea of energy marked by the faintest of quantum ripples. Given enough time and the unwavering operation of gravity and dark matter, that subtle pattern was destined to grow into the grand design we observe. This reveals a cosmos that is fundamentally comprehensible, where the same physical laws that govern a falling apple here on Earth also sculpt the largest structures in existence. There is a powerful elegance in this realization, a sense that the universe operates not through caprice, but through a deep, underlying order that we are capable of uncovering. This inherent order challenges a purely random view of cosmic history. The galaxies are not scattered like confetti. They are organized, strung along invisible threads, and gathered into clusters with a statistical regularity that speaks of a guiding process. This is not the hand of a designer in a traditional sense, but the unmistakable signature of self-organization. the universe, starting from a simple state, possesses an innate tendency to create structure. Gravity acts as the great sculptor, but the potential for the web was written into the fabric of space-time from the beginning. It is a universe that builds itself, following a recipe encoded in its own fundamental constants. From the quantum realm to the galactic scale, we see a chain of cause and effect, a narrative of growth and transformation that feels less like a random series of events and more like a single, unfolding story. The web is that story written large across the sky, a testament to a cosmos that generates intricate beauty through the patient application of its own internal logic. For us, living on a small planet orbiting an ordinary star in a quiet galactic suburb, this perspective is both humbling and strangely connecting. The feeling of smallness is undeniable when confronted with such scale. We are inconsequential in terms of size and duration when measured against the web's vast expanse and billion-year evolution, yet the science reveals a deeper, more intimate connection. Every atom in our bodies that is heavier than hydrogen or helium was forged in the heart of a star. That star and the galaxy it belonged to did not form in isolation. It was assembled over eons from gas that flowed along the dark matter highways of the cosmic web. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in stellar furnaces and then scattered into space, eventually finding their way along these gravitational currents to become part of our solar system, our planet, and us. We are not just observers of this vast structure, we are products of it. Our very substance is stardust that once traveled the cosmic filaments. This realization transforms the web from a distant astronomical curiosity into a part of our own origin story. We are embedded within this network, both literally and figuratively. The same laws that shaped it also govern the chemistry of life and the physics of our world. Contemplating this can evoke a sense of cosmic kinship, our understanding that we are not separate from the universe, but an expression of its long, structured evolution. We are the universe in one particular arrangement, becoming conscious of itself and beginning to trace the invisible threads of its own magnificent architecture. The philosophical weight of the cosmic web, therefore, lies not in providing easy answers, but in framing profound questions about order, emergence, and our own fleeting, yet deeply connected, place within an ancient and ongoing construction. The cosmic web is our universe's ultimate masterpiece, a structure of breathtaking scale and profound simplicity. We have traced its origins to the faintest quantum whispers, watched gravity sculpt its dark matter skeleton, and followed the flow of luminous matter along its silent highways. This journey reveals a cosmos not of random splatter, but of deep, elegant order. The invisible filaments solve the ancient mystery of galactic placement, explaining why brilliant cities of stars gather in specific regions while vast deserts of nothingness stretch between them. This understanding transforms the night sky from a scattering of isolated points into a single, coherent map, a living atlas of cosmic evolution. More than just solving a puzzle, this grand architecture has become our most powerful instrument. By measuring the precise spacing of its threads and the growth of its voids, we can weigh dark matter, measure the push of dark energy, and even sense the ghostly presence of neutrinos. The web is a cosmic laboratory, allowing us to test the fundamental laws of physics on the largest possible canvas. And in this magnificent design, we find our own place. Our Milky Way galaxy is not an island drifting in a formless sea. It is a traveler on a filament, a suburban resident in a quiet neighborhood of the Virgo supercluster. The atoms that compose our world, forged in generations of stars, were once carried along these same gravitational currents. We are, in every literal sense, children of the cosmic web. Its structure made our stable corner of the universe possible, offering the billions of years of peaceful evolution needed for planets to form and life to emerge. As our telescopes grow ever more powerful, mapping this tapestry in finer detail, we are not just charting distant space, we are reading our own cosmic genealogy, learning how the largest forces in existence conspired to create a small, conscious vantage point from which to admire the view. The universe built a web, and in doing so, it built a home.